Okay, so today is the 3rd, 2/4/15. Wow. Happy post-Groundhog Day. So, we did this. This is where we left our chemistry heroes, that you can do what we call formula mass. It can be a molecular mass. Same way you did molar masses. And the next idea is that we can do conversions. And I think we talked about this briefly. Yes? Okay. Did we do a sample problem on this together? No? Okay. So, if I were to give you 250.0 grams of calcium chloride. So calcium chloride is a seasonal topic because if you look at the ingredients on a lot of ice melt products, some of them are calcium chloride rather than sodium chloride, and so it's a seasonal thing. How many moles of calcium chloride is that? Whoops. That's what we want to know. So the first thing that we would start off with always is what? When we do any kind of molar mass conversion, what always goes in the very first box? Are given. So we would start off with 250 grams of calcium chloride, CaCl2. Now, what units in chemical are going to go down below to cancel? Grams of calcium chloride. And we want to end up in moles. What units in chemical will go up top? Moles of calcium chloride. Well, the number that we're missing is that molar mass number. So this is where we pull out the periodic table and the calculator and do a little bit of math. So calcium is 40.08 grams per mole times 1. Chloride ion is 35.45 grams per mole times 2. So 40.08, and what's that? 70.90, I think. So 70.9, is that right? 35.45 times 2? Yeah, 70.90. Okay, plus 40.08. Okay, so we get 110.98 grams per mole. So 110.98 grams of calcium chloride and 1 mole of calcium chloride. And now it's just down to division. 250 divided by the number we just got. And we get 2.25265, etc. How many sig figs do we get? 4. So we're going to go with whatever's here as our last digit, and the next digit is a 6, so we get 2.253 moles calcium chloride would be our final answer. Not significantly different than the compositional stoichiometry that you've already done. The only difference is that now you need to do this step. You need to add up the formula mass. So pretty easy. Really. These are the kinds of practice problems that we just did one example of it. We did how many moles were in a set number of grams. We could do how many molecules are in a set number of grams. We could do the mass of a given number of molecules. I'm going to leave you to practice those in your homework on your own. We're not going to do a lot of practice together because we're kind of, well, we were behind and then we lost a couple more days. So if you need help on practice with these, come see me after school, Tuesdays. Okay, so this is percentage composition problems. And what we're looking at is the percentage by mass of a compound that's made up of a given element. This is important actually mostly in the inverse, because when we find new substances, so if you think about like the Mars rover programs, you've got these little robots on the face of Mars scooping up chemical samples and running them through a chemical analysis, and it comes back and says, this compound found is this percentage iron, this percentage silicone, this percentage oxygen. Well, from that information, you need to be able to derive a chemical formula. And so we're going to start off doing it sort of, in essence, backwards to the way it's typically used in the real world, because it's easier to understand that way, and then we'll do it forwards. Okay, so all this is, you are looking at the mass of a given element that's in 1 mole of a substance divided by the molar mass of the compound. And we can find the percent composition of sodium in sodium chloride. So let's do that first. So what we imagine is that we have 1 mole of sodium chloride. Okay? And in that mole of sodium chloride, how many moles of sodium do we have? How many moles of sodium ions do we have? 1. Because it's just NaCl. So we know that 1 mole of sodium has a mass of what? Yep, 22.99 grams. And 1 mole of sodium chloride, I'll move this down, has a mass of what? Well, 22.99 plus 35.45, 58.44 grams. So what percentage of the mass of sodium chloride is made up of sodium? Well, that's easy. Yeah, overrated. Let's move that up. Okay, so we get 0.393394, etc. If we multiply that by 100, we now have a percentage. So the percent composition of sodium in sodium chloride is 39.34. Or you can say NaCl is 39.34% sodium by mass. Okay. Let's do one that's got more stuff. So what's the percent composition of carbon in glucose? Whoops, I screwed that up. There. Okay. Well, we start off with okay. So in every 1 mole of glucose, how many moles of carbon are there? 6. 1 mole of glucose has got 6 moles of carbon atoms. Because in every molecule of glucose, you have 6 carbon atoms. So 6 moles of carbon in 1 mole of C6H12O. Darn it, I just keep wanting to do that. Well, what's the mass of 6 moles of carbon? Which is the molar mass of carbon times 6. So 12.01 grams per mole times 6, we get 72.06. And the mass of 1 mole of C6H12O6. We've got the 72.06. We've got plus So that's 72.06. This is 12.12. And we've also got oxygen, which is 16 times 6. Okay, so the mass of 1 mole of glucose is 180.18 grams. Okay, 72.06 divided by 180.8. Okay, so what we find is that glucose, and of course we'd have to multiply, so the number we get is 0.3999334. 4 sig figs? Yeah, 4 sig figs. So 39.99% carbon. Okay. Shrink that. So we could say that glucose, C6H12O6, is 39.99% carbon. I swear there are things that don't come out to 39. There really are. Fairly straightforward. Want to do one more together? Okay. Everybody got this? I can flip the slide? Okay. All right. So, what if I just give you one that says, find the percentage composition of a compound? Then in the last two we've said, what is the percent comp of sodium in sodium chloride? What's the percent comp of carbon in glucose? Well, what if I just say, find the percentage composition of H2O? That means you need to find the percentage composition of each of the elements that's present in the compound. So here we're going to start off, we might as well just go ahead and do the molar mass of H2O. So we've got 2.02 plus 16, 18.02 grams per mole. One of those things that you'll just commit to memory. So for the hydrogen, how many moles of hydrogen are there in 1 mole of water? 2. There are 2 moles of hydrogen in every 1 mole of water. Okay, so 2 times 1.01 grams per mole, 2.02 grams of hydrogen in 18.02 grams of water. Okay, what do you get? Somebody who has shoelaces. You want to take it? No? No calculator. You sat down without a calculator. What a brave and foolhardy thing to do. Get yourself one. Okay, who else has shoelaces and an answer? Mr. Johnson.
I have also a calculator.
Really? Quite foolish of you, I would say. Oh, and there's a sudden race to the calculators.
097.
112097, etc., etc., etc. So if we multiply that by 100 to get our percentage, water is 11.2. Oh, we don't have 3 sig figs because of that. So it's 11.2% hydrogen. Then we could say H2O is 11.2% hydrogen. Okay, what's the percentage of oxygen in water? Let me tell you what I don't want to ever see you do. Oh, 100 minus 11.2. No. Though that's a great way to ballpark it and know approximately where your answer should reside, I expect you to do, let's see, 16.00 grams of oxygen in every 18.02 grams of water gives us 0.887902331, so 88 88.8. Actually, we could use 4 sig figs there. Huh. Yeah. 88.79% oxygen in water. Okay. Clear? Fairly straightforward? Okay. There will be, well, let's see. Hold 1 second. Why we do percentage composition? It's pretty much all down to analytical chemistry. It is the way that you get a formula out of an unknown substance. And there are unknown substances, well, I don't know if they're being discovered all the time at this point or not. We've analyzed a lot of the world. But there are still novel substances, or you find a substance and it may be a substance that's known, but it hasn't been previously identified in a particular setting. So when you find something that you don't know what it is, there are ways to analyze how much of it is made up of different elements. All the elements have a signature based on the size of their nucleus. You can do several different kinds of analysis. You can do nuclear magnetic resonance imaging, and you basically vibrate it. You put it in a little tube, you stick it in a big machine, you hit the big go button, and it vibrates the nucleus in a strong magnetic field, and it will give you a readout that basically, if you know how to read it, you can tell what's in there. It gives you spikes at different locations. There are a couple other ways. There's chromatography, and you can look at the color of light that is emitted from something when it's hit with energy of a certain frequency. You can do all kinds of things, but we're finding new things all the time, and the information that you preliminarily get is just the percentage of the different elements. So this is why we use percent comp. Now, to do these problems in the direction that they're actually done in the real world, you don't get the formula and figure out what percentage they are. So that's really great for understanding what percent comp is. But in the real world, what you get is just the percent comp, and what you have to find is what's called the empirical formula. So the empirical formula is the smallest whole number ratio of the atoms in a compound. Obviously, empirical formulas are only used for molecular or ionic compounds. Ooh, good. We have. So I'll tell you this. Well, okay. How many of you would say that empirical formulas are only meaningful when we're talking about molecular compounds? How many of you would say they're only meaningful when we're talking about ionic compounds? Ah, how many of you are too chicken to commit to a position? No. An ionic formula is already an empirical compound. An ionic formula is already the simplest whole number ratio. A molecular formula, of course, represents an actual molecule out there in space, out there in some substance, out there in a bag of sugar, and so we can simplify that down to an empirical formula. So let's do some examples of empirical formulas. Okay, we'll use everybody's favorite, C6H12O6, glucose, the simple sugar that your cells use. This is a molecular formula. This is an actual literal representation of one molecule of sugar. One molecule of sugar is 6 carbons chained together like a little piece of crochet, atomic crochet. Now there's an idea. It's not a simple whole number ratio. This can be simplified. So the empirical formula, so this is a molecular formula. This is a molecular formula. The empirical formula for glucose would be what? It's the simplest whole number ratio. If you simplify that down all the way, CH2O. Okay? Now, an empirical formula has the symbols. Okay? It's still a type of chemical formula. So this is an empirical formula. You very often see these with the big hydrocarbons. Hydrocarbons are things that are made up of. We'll do a couple examples that involve hydrocarbons. Well, let's see. We can get a really crazy long chain hydrocarbon like C10. Would that be H? Hold on. Okay, so C10H22. We'll talk about it when I see you after lunch.